science at NASA. Quantum foam. It may sound like the name of a new craft beer, but it's something even more amazing. To see it, you have to dive down the rabbit hole of quantum mechanics, a branch of physics that describes how light and matter behave at atomic scales. In this bizarre realm, matter can be in two places at once. Electrons can behave as both particles and waves, and Schrödinger's cat can be alive and dead at the same time. Or so the quantum theorists tell us. Theirs is a world wildly different from Einstein's. In his highly successful theory of general relativity, Einstein tells us that energy equals mass, and mass warps space-time. Remember the physics analogy of the trampoline with a bowling ball in the middle? Like that ball, which gently distorts the trampoline's canvas, the sun warps the smooth canvas of space-time enough to make planets move in curved orbits. A whole galaxy warps space-time much more. The more massive the body, the more warping. But if we could zoom in on the quantum realm, we wouldn't see a smooth expanse of canvas gently distorted by massive bodies. We'd see quantum foam. Quantum gravity models predict that space-time is a seething foam of tiny regions where minuscule new dimensions unfurl and then furl back in on themselves, spontaneously appearing and disappearing with inconceivable quickness. These regions blink in and out of existence like the bubbles in the foam of a freshly poured beer. There's no such thing as empty space. There is only quantum foam everywhere. Such is space-time for a quantum physicist. Eric Perlman of the Florida Institute of Technology says the bubbles in the quantum foam are quadrillions of times smaller than atomic nuclei and last for infinitesimal fractions of a second, or in quantum speak, the size of a Planck length for a Planck time. According to string theorists, this requires an additional 6 dimensions. Space-time itself is fluctuating in these regions. But this is all hearsay. We can't see this quantum foam in all its weird glory. Researchers have to look for evidence of its effect to prove it's there and determine its nature. Perlman and his colleagues recently attempted to do so by using X-ray and gamma-ray observations of distant quasars by the Chandra X-ray Observatory, Fermi Gamma-ray Space Telescope, and the Very Energetic Radiation Imaging Telescope Array System, or VERITAS. Because these bubbles are so small and last for such a short time, they can never be observed directly, says Perlman. But they would affect light in an interesting way. Each photon's path would be slightly different as it maneuvered through the all-pervading myriads of tiny fluctuations frothing up space-time. And as a result, the distance each photon travels would be different. Perlman says that over the cosmological distances that the photons travel from these distant sources, the effects of the fluctuations the photons encounter will accumulate. The more they accumulate, the more out of phase the light will get. Creating an image from a collection of such photons would be like trying to distinguish what one person is saying in a huge crowd of people talking. So it would be physically impossible to get a clear picture. But the findings of Perlman and his team took a bit of the fizz out of the quantum foam. It seems space-time has to be smooth, at least at the level of 1,000 times smaller than an atom, and space-time must be much less foamy than most models predict. But, he cautions, this investigation does not go as far down as the Planck length, so there is still some hope for the tiniest of bubbles. For more news about quantum foam and other mind-bending NASA research, stay tuned to science.nasa.gov.
Make me feel So, what are we really made of?
Dig deep inside the atom and you'll find tiny particles held together by invisible forces. Everything is made up of tiny packets of energy born in cosmic furnaces.
The atoms that we're made of have negatively charged electrons whirling around a big, bulky nucleus.
The quantum theory offers a very different explanation of our world.
The universe is made of 12 particles of matter, 4 forces of nature. The universe is made of 12 particles of matter, 4 forces of nature. That's a wonderful and significant story.
Suppose that little things behaved very differently than anything big. Nothing's really as it seems. It's so wonderfully different than anything big.
The world is a dynamic mess of jingling things. It's hard to believe.
The quantum theory
It's so strange and bizarre. Even Einstein couldn't get his head around it.
In the quantum world, the world of particles, nothing is certain. It's a world of probabilities.
The quantum theory offers a very different explanation of our world.
The universe is made of 12 particles of matter, 4 forces of nature. The universe is made of 12 particles of matter, 4 forces of nature. That's a wonderful and significant story.
It's very hard to imagine all the crazy things that things really are like. Electrons act like waves, no they don't exactly. They act like particles, no they don't exactly.
We need a theory of everything, which is still just beyond our grasp. We need a theory of everything, perhaps the ultimate triumph of science.
The quantum theory offers a very different explanation of our world.
The universe is made of 12 particles of matter, 4 forces of nature. The universe is made of 12 particles of matter, 4 forces of nature. That's a wonderful and significant story.
I gotta stop somewhere. I'll leave you something to imagine.